this lecture we will study how passivity can be used to stabilize the origin of a system by output feedback. Okay. So consider the following state equation. X dot equals f of xu, and the output is described by the function h. Okay, so this is our system 1, where the sizes of the variables are as follows. X is in Rn, u, y, input and output, they're of the same size. Okay, Rm, and plus the usual assumptions that f and h are 0 at 0, and their local dimensions, f, h. Okay. Now for this setup, what we want is, we want to figure out a function, okay, of y, such that if we choose that function as our input and feed that signal to the system and obtain the closed-loop, the origin of the closed-loop system is asymptotically stable. So that's our goal. Okay, so what we want is stabilize the origin by output feedback. U equals minus then some function of the output y. That is, okay, in other words, what we want is the origin of the closed-loop system x that equals f of x, and u is minus phi of y, and y is h of x. Therefore, the closed-loop system in terms of x is h of x, okay, is stable and preferably asymptotically stable. Okay, now for this, a very useful result, which has a very straightforward demonstration, is the following theory. It's 40.4 from the text. Suppose that the system 1 satisfies the following properties. It's passive with a radially unbounded positive definite storage function. Okay, and it's zero state observable. Okay, so what zero state observable was you said, suppose that you consider a situation where both the output and the input of the system are identically zero. Then if the system is zero state observable, that means the solution must be sitting at the origin. Okay, so x of t must be identically zero in that situation. If that's the case, then we call such systems, remember, zero state observable. Now, under these two assumptions, the origin x equals 0 can be stabilized by u equals minus phi of y, where the mapping phi satisfies the following properties. where the map should be from Rm to Rm, because what it does is it takes the output and produces the input. Since input and output, they are of the same size, we're talking about a mapping from Rm to Rm. Is any local Lipschitz function satisfying phi 0 equals 0. Okay, so it's 0, it's 0, and it satisfies this positive definite with respect to y kind of property. Okay, y transpose phi of y is always positive except when the output is 0. Okay. So this system, we are assuming that satisfies those two properties. Okay, it's passive, and the storage function is radially unbounded and positive definite. And also, we are assuming that it's zero state observable. So if those two conditions are met, then it's very easy, the theorem claims, to stabilize the origin of the closed loop system by output feedback. All you have to do is pick any mapping, okay, phi function that has this positive definiteness property with respect to the output, with respect to its argument, and then set u equals minus that function of phi and close the loop, and the origin of that system becomes stable. In particular, thanks to radial unboundedness and positive definiteness of the storage function, we have global asymptotic stability for the origin. Okay, so in particular, the origin of the closed loop system, x equals f of x minus phi of h of x is globally asymptotically stable. Okay. Now, what we're going to do is we're going to prove that theorem, which has a very simple, short proof, and then we will move on to some other situations where we're going to be considering systems that do not satisfy directly the conditions that are listed in the theorem. So then we're going to try to figure out how we can make, through some simple tricks, certain modifications on the system so that it becomes, the new system satisfies the conditions of theorem 14.4. But first, let's convince ourselves that this statement is indeed true. Okay, here goes the proof. Let V be the storage function of our system. Okay. Be the storage function. And, well, by assumption, it's positive definite and radially unbounded. Then set the input to minus phi of y, and phi is any mapping that satisfies that positive definiteness with respect to y type of condition. Then what we have is b dot less than or equal to the inner product of input and output. So that's the definition of passivity. And now what we're doing is we're choosing input to equal minus phi of y. So what we have is minus y transpose phi of y. So this always upper bounds time derivative of the storage function along the solutions of the system. And this clearly is negative semi-definite, because this thing is positive definite with respect to y. So V dot is negative semi-definite with respect to the state, at least. Okay, and V dot, when it's identically zero, okay, time derivative of the storage function is identically zero, it's clear that it's only possible when the output is identically zero. Okay, because V dot is upper bounded by minus y transpose phi y. Then we can invoke zero state observability and proceed as follows. Okay. Suppose that the output is identically at zero. Okay, so we consider the case V that equals zero. Okay, so we try to figure out the largest invariant set within V dot equals zero. Okay, if we show that that largest invariant set is the origin. Okay, the only possibility that this is satisfied identically is that the solution is sitting on the origin. Then by invariance principle, we would have asymptotic stability. And thanks to radial unboundedness, we can extend that result to global asymptotic stability. Okay, so let's analyze V dot equals zero. Okay, so V dot equals zero implies the output is at identically zero. Okay, and then the input is identically zero because U equals phi of y, and when the output and input are identically zero by zero state observability, it must be that the state is identically zero. Okay. Hence, we have obtained the following. Okay, so we have V, which is by assumption positive definite and radially unbounded. Okay, by passivity, we obtain that V dot is negative semi-definite, and then we analyze the situation where V dot is identically zero, and using zero state observability, we figured out that that implies that this solution is at the origin, okay, when this is satisfied. And combining all these yields, x equals zero, it is global asymptotically stable. Okay, so the origin is global asymptotically stable thanks to Lassalle's invariance principle. Lasalle and Krasovsky's invariance principle. Now, as we said, we're gonna look at the situation where the assumptions of, or the conditions listed in the theorem are not satisfied. Okay, what can be done in that situation is the question we will now try to answer. Okay. What if the assumptions of our theorem are not directly satisfied. Okay. And possible answer to that question is, then we may try if we are allowed to, that is, choose, if possible, a different output. Okay. It may or may not be possible, but if it's possible, then it's definitely a way to go. Work with another output. And another way to go is work with another input. Okay, we define the input. Okay, now we're going to see how those alternatives can be employed. Consider first a special case of the system. Okay, so that's the system of theorem 14.4. Now, in that system, the right-hand side was general, that is x that equals f of x u. Now we're going to consider a special f of x u, namely, we're going to suppose that the right-hand side is f of x plus some function of state multiplying the input. Okay, g of x times u. This could be a scalar, or this could be a matrix, a square matrix. Excuse me, not a square matrix. It should be a n by n matrix. That's a function of x. Now, again, we will make some assumptions. Suppose there exists a radially unbounded positive definite with respect to state function v such that time derivative of that function, okay, along the solutions of the system when the input is set to 0, okay, in other words, this inner product, note that the right hand side becomes f of x only when you set the input to 0. Okay, so this is never positive. Okay, so this would directly give us the following fact: when if you set the input to 0, then the system x that equals f of x is the origin of that system is stable. Since there is no indication about negative definiteness or negative semi-definiteness, we cannot say anything at this point about asymptotic stability. Okay, under that assumption. And then suppose further that we are free to choose the output that we want to work with. Suppose that that choice is a design parameter. The output y equals h of x. So h is to be designed, suppose. Now here is a suggestion for how to choose the function h. Choose, for instance, h of x as gx transpose times the gradient of v, okay, with respect to x. Now, why that choice is meaningful, at least in the light of theorem 14.4, So let's see. Okay, with that choice, we can proceed as follows. V dot equals inner product of gradient of V and the right hand side of the system. So f of x plus g of x times u. And then this can be written as two separate inner products, f of x plus g of x u. Okay, and then that's less than or equal to, note that this is never positive by assumption, therefore we can remove that and upper bound be that by the remaining term. Okay, so we have therefore this inner product which reads u transpose gx transpose times gradient of the function v. Okay. And that equals, under this choice, u transpose times h of x, and h of x is our output. Therefore, what we have is, okay, v dot less than or equal to u transpose y. Okay, so what we have therefore is, we have that with this particular output and with this particular storage function, the system is passive. Okay. Furthermore, storage function that we're using is radial and bound and positive, okay, by assumption. So, by choosing the output cleverly, we have, well, if that's possible, if we can choose the output, we have made the system passive. Okay. Hence, V dot is upper bound by V, inner product of input and output, and the system x that equals f of x plus gu and y equals h of x is passive. Okay, this is a passive system. So all the conditions of theorem 14.4 except zero state observability are satisfied if, furthermore, with this choice of output, the system is zero state observable. If that can be shown, if that is satisfied, then we can now invoke theorem 14.4 and claim that by a negative definite through a proper phi function, this system can be the origin of this system can be globally stabilized by output feedback. Okay. So let's put that conclusion down. If it is also zero state observable, then the assumptions of theorem 14.4 are satisfied. In that case, we know how to stabilize the origin. Okay, so let's exercise that approach on a very simple second order example. x1 dot x2 dot minus x1 cubed plus u. Okay, the output of the system is not given because we are assuming that it's a choice, it's a design parameter. So we're gonna choose by first guessing a right storage function. We're gonna choose the output so that the system is passive. Okay. With respect to that output. So let us consider the following storage function candidate: 1 over 4 x1 to the 4 plus 1/2 x2 squared. Okay. And let's look at the time derivative of that candidate v dot. Then v dot is x1 cube times x1 dot plus x2 times x2 dot. x1 dot and x2 dot are here. So what we have is x1 cube times x1 dot, which is x2, plus what? x2 times x2 dot, which is minus x1 cube plus u. Now this and that, they cancel, and what we're left with is input multiplying something, and that's something, if we choose it as our output, then what we have is v that equals the product of input and output, and then we have a passive system with storage function here, which is clearly positive definite and radially unbounded. Okay. That equals x2 times u. Now, this immediately suggests that the output should be chosen as the second state variable. Okay, y equals x2, then v dot equals uy, okay, or u transpose y. Well, in that case, it doesn't matter whether we do transposition or not, because everything is scalar. And the system from that output is passive. Okay. Let's also check zero state observability from this particular output. Okay. If we also have zero state observability, then the conditions of theorem 14.4 are satisfied, and it will be quite straightforward to come up with a stabilizing output feedback law. So, to check zero state observability, what we do is we consider the case where both the input and output are identically zero. Okay? The input is identically zero, the output is identically zero, and let's figure out the implications of those two constraints. If the output is identically zero, so that means x2 is identically zero, because x2 is our output. So x2 is identically zero. x2 identically zero means its time derivative is identically zero, because x2 is constant, therefore it must have zero derivative. Okay. That implies, if you look at the second state equation, this is identically zero, the input is identically zero, therefore minus x1 cube must be identically zero, and that's only possible when x1 itself is identically zero. x1 identically zero. Therefore, when both the input and output are identically zero, it must be that the state x of t must be identically zero. Therefore, the system is zero state observable. Hence, the system is zero state observable from output y equals x2. Okay. And now all the conditions for theorem in theorem 14.4 are satisfied, and we can now easily design an output feedback law to global-less perfectly stabilize the origin of the closed loop. Choose, for instance, u equals minus k x2, okay, minus k times y. In this case, the phi function would be linear, just k times y. Clearly it satisfies the conditions in theorem 14.4. But it doesn't have to be linear. or we can choose u equals minus b times x2. Okay, so it's locally linear, okay, around the origin, but if you further increase the output, it just saturates, but nevertheless, still that function also satisfies the condition that should be satisfied by phi. Okay, with kb positive. Then the origin of the closed loop system is globally, asymptotically stable. With this choice, or that choice, or anything that you can come up with a proper phi theorem. Okay. Now, in this example, and what we did was we have chosen the output, if it's possible, so that the system from that output satisfies some nice passivity properties. Now we're going to look at the other angle, okay, other side of the problem, and now we will investigate what can be done about choosing the input, re-choosing the input, or redefining the input, so that with that new input the system becomes passive. Okay. So our new question is the following. What if the framework that we looked at recently, which was f of x plus g of x u and y equals h of x, is not passive with the proper storage function, by which we mean positive definite, radially and bounded storage function. Okay, here is a possible answer to that question. We can try feedback passivation. Okay, so in a sense we're introducing feedback twice. In the first time to make the system passive, and then the second time to stabilize the origin of the new system. Okay, and that's called feedback passivation. That is, choose if possible u equals a function of this form, alpha of x plus something that multiplies v, and v is the new input variable, okay, that from which we will try to make the system passive. Okay, so v is the new input. Such that the new system x dot equals f of x plus g of x times u, and now we're expressing u as sum of those two terms. X plus g of x beta x times v, and y is h of x. Okay, now this new system satisfies the assumptions, conditions of theorem 14.4. Okay, now we will apply this idea on some particular system, okay, namely M-Link robot manipulator, and to see what's meant by this suggestion here. Here is our example. It comes from the real world. It's M-Link robot manipulator. Okay, so we're talking about a system of order 2 times that number of lengths. Okay, here is the system in its original form. Okay. Some matrix, which possibly is a function of Q, okay, the positions or generalized positions, times the acceleration Q dot plus the velocity terms Q dot times Q dot plus dQ dot plus term possibly representing the gravitational effects G of Q, and on the right hand side we have the control input U. Here we have Q in Rm, G is a function from Rm to Rm. All others are matrices M, C, D, R squared matrices, okay, N by M, and they satisfy the following properties. N equals M transpose and that's greater than epsilon times identity for all possible Q's. Okay. So it's a symmetric matrix and it satisfies greater than epsilon identity. It simply means that, okay, if 2 square matrices, symmetric square matrices satisfy this, we write this, okay, A greater than B, to mean that A minus B, this matrix is positive definite, okay? Okay, so M satisfies that, and N dot minus 2C is symmetric. Okay. And the constant matrix D minus D equals D transpose greater than equal to 0. The constant matrix D is symmetric and positive semi-definite. By N dot we mean the time derivative of this matrix when considered as a function of time, which defined as M of Q of T. Okay. So those are the assumptions. Now for this robot, what we want is, we want the arm move to some given reference point and stay there. Okay. So we want, this is our design goal, stabilize point Q dot equals QR 0. Okay, so the position goes to some fixed reference position, which we denote by QR. QR is fixed, and at that point we want the robot arm stay put. Okay, stay fixed. Therefore, all the velocities must be 0. That's what we want. So QR is a fixed reference position. Now, for this system with that goal, we want to achieve our goal through the passivity-based approach. For that, let's move on to new coordinates, so that with respect to the new coordinates, the problem becomes that we want to stabilize the origin. Define the error, that is distance to the desired state, E equals Q minus the reference position QR. In that case, E dot, the velocity of the error, is simply Q dot minus QR dot. QR is fixed, therefore its time derivative is 0. That means E dot simply equals Q dot. Okay. Now we can consider E and E dot together as a single vector in R2n to be our new state, and we want to stabilize the origin with respect to that new state, new coordinates. Okay, so now we can rephrase the statement in terms of our new coordinates. Now we want E dot to converge to 0, converge to the origin, or the new origin. Now let's write the system, or re-express the system in terms of our new coordinates. We can write n of q, let's keep this q as q, E double dot. Okay, since E dot is Q dot, E double dot is clearly Q double dot plus C matrix Q dot times E dot plus D E dot plus G of Q, that equals U. Okay, so this is our system 1 in terms of the new state, the error state. System 1 is not passive. Okay, no matter what storage function that you choose, no matter what input that you choose. Why is that? Regardless of the output. With any definite radially unbounded storage function. Because, okay, now consider storage function. V is positive definite. And if the system, okay, if that system were passive with respect to that storage function, then what we would have is, and you can choose any output you want, what we would have is V dot less than or equal to the product of U and Y. Okay? So if you set U to 0, therefore what we have is V dot less than or equal to 0. And V is a positive definite function. Therefore that would mean the origin is stable. Okay? Now, the origin is not stable, but that's not true, because if you set U equals 0, what we have is, at the origin, that is E and E dot, they're all 0. These terms disappear, and what we have is G of Q equals 0. Okay, at E equals 0, G of Q is G of QR. Okay, so what we would be having is G of QR equals 0. But QR is an arbitrary fixed reference position. Therefore, in general, G of QR should not be 0. Hence, we simply don't have passivity because the origin for this system, when the input is 0, is not actually an equilibrium point. Okay, since it's not an equilibrium point, it's meaningless to talk about its stability properties. Because E dot equals 0 is not even an equilibrium point. For U equals 0. So therefore, we have to redefine input so that when that input is set to 0, this guy becomes an equilibrium point, and then after that, we can try to work out how that equilibrium point can be made asymptotically stable. Okay, so this is the approach. Let us introduce a new input variable V such that we have plus V, this relation. Okay, so this is V and this is the original input. And we choose V, we define V such that V equals U minus this term here. With P is a square matrix. And we choose it, okay, we design it so that it's symmetric positive definite. Okay, later on, this matrix will be used in constructing our storage function. Now, let's rewrite the system in terms of our new input. Then we have ME dot dot plus C E dot plus D E dot plus KPE equals V. Okay, so you replace this U with this term. This GQ and this GQ will cancel one another, and then you can throw this minus KPE to the other side, and what you have is something equals V. So this is the new expression of the system in terms of the new input variable V. Okay, so let's call this system 2. Now with this new system, when you set the new input to 0, this E dot equals 0 satisfies the differential equation, therefore it's an equilibrium point. Okay? And now what we want to do is we want to stabilize that equilibrium point, and for that we're going to use passivity-based tools. And hence, there are two things that we should do. First, we have to figure out a clever storage function which can be used to establish stability, and then by help of that storage function, we will have to pick, or we will choose the output. The output of the system is still undefined. Okay, and then hopefully, with that proper storage function and the appropriate output that will be chosen by looking at the time derivative of that storage function, we will be able to put the system in a form so that the conditions of theorem 40.4 are satisfied. And then once that's achieved, it's easy to write down the stabilizing feedback law. Okay, so the very first step therefore is, what's the storage function? So here, this seems to be a working alternative. V E dot equals 1/2 E dot transpose M of Q E dot plus 1/2 E transpose KP E. Okay? Now this is, with respect to state E dot, is a positive definite and radially unbounded function. Okay? Because this, even though it's a function of Q, in particular function of time, it's always symmetric, positive definite, and it's always greater than epsilon, some fixed positive number times identity matrix. And this is by choice, by design, also positive definite matrix. Therefore, the overall expression is positive definite with respect to the error state, E dot. Okay, now let's write down V dot, and by looking at that expression, we will have some ideas on how to choose the output. Okay, so that we have some nice passivity properties. V dot is so V dot is excuse me. V dot equals, okay, this dot plus this dot. Okay, now this dot is by chain rule. Okay, 1/2 E double dot transpose M E dot plus E dot transpose this dot E dot, and finally 1/2 E dot transpose this times E double dot. Okay, the first and the third terms can be combined because they are the same, and we can then get rid of this 1/2, and that reads E dot transpose MQ E double dot. As for the middle term, you would have plus 1/2 E dot transpose M dot Q E dot. Okay, so this whole thing is the time derivative of the first term in our storage function. And then we have the time derivative of this, which is E transpose KP E dot. Okay. Now we can proceed as follows: E dot transpose. Now here we have and E double dot, and we can express that as minus this, minus this, minus that, plus V, okay, using the equation. So what we have is minus C E dot minus D E dot minus KP E plus the new input plus 1/2 E dot transpose M dot E dot plus E transpose KP E dot. Okay. Now E dot transpose KP with a minus sign in front, and this guy will cancel. Okay. And what else? We can reorganize certain terms and write 1/2 E dot transpose M dot minus 2C E dot minus E dot transpose D E dot plus we have E dot transpose times V E dot transpose times V. Okay. Now this term is 0 regardless of E dot, because this matrix we're told is skew symmetric. Okay. And that minus 2C. If you take a skew symmetric and multiply from right and left with the transpose and itself of the same vector, then you obtain 0. Because M dot minus 2C is skew symmetric. Okay. Skew symmetric means that a matrix equals the minus of its transpose. Okay. And what we have is, and therefore this is less than or equal to, this term disappears, and D is a positive definite or positive semi-definite matrix over this negative semi-definite term, and we can just ignore it and upper bound everything by simply that inner product of E dot and V. Okay. E dot transpose V. Okay. We call E is positive semi-definite. So once again, by skew symmetry of this term and positive semi-definiteness of D, we were able to upper bound V dot by inner product of E dot and V. That immediately suggests that we should pick the output as E dot, so that we have V dot, the time derivative storage function, is less than or equal to inner product of input and output. V dot less than or equal to E dot transpose times V. Now choose the output as E dot, then system 2, which is the origin system expressed in terms of the new input and new coordinates, V and E respectively. System 2 is passive with a positive definite radially unbounded storage function V. Okay, storage function sits here. How about zero state observability of the system? If that's also satisfied, then we have everything we need to apply theorem 14.4. So what we consider is the case when both the input and the output are identically zero. And from this, we want to achieve, if we may, that both E and E dot must be identically zero. If that's the case, then the system is ZSO, zero state observable. Now output 0 implies that E dot identically 0 because it's our output. Okay. Clearly, that means E double dot identically 0. And then, if you plug in E dot equals 0 and E double dot identically 0 to system equation, system 2, also V is identically 0, and what you have is, you have to have error must also be 0. Okay. Therefore, system 2 is 0 state observable. Okay. Now, let's choose the input as minus phi E dot of E, as suggested by theorem 14.4, with phi satisfying properties that is 0 at 0, and E dot transpose phi E dot always positive for non-zero E dot. Then the origin of E dot, okay, the origin that we want to stabilize is globally asymptotically stable by theorem 14.4. Okay. Now let's translate everything into the original. In terms of the origin variables, which we had Q and U, and then we'll be done. Okay, now the original input reads U equals GQ minus KPE plus V, and now V we're choosing to equal minus phi of E dot, minus phi of E dot. Therefore this is U. And let's also get rid of E's. So what we have is G of Q minus KP times this difference, because that's how we defined error, E, Q minus the reference position, minus phi of Q dot, because E dot and Q dot, they're the same thing. Okay. And here is a special case. U of Q equals G of Q minus KP Q minus QR minus KD Q dot, where KD is a positive matrix, okay? So in that case, phi is simply KD times E dot. Clearly it satisfies the property that it should satisfy. Yes. KD is an n by n matrix, which is symmetric and positive. This would be, therefore, a very nice choice to stabilize the reference position QR for the n-link robot manipulator.